Welcome to the linear systems lesson in the series, The Shape of Space, Linear Algebra. In the very first lesson in this series, I talked a bit about solving linear systems, and I mentioned several different cases where we had one solution, we had no solutions, or where we had an infinite number of solutions. And I would encourage you to review that first lecture if you haven't already. In this lecture, what I want to do is relate linear systems to what we've learned about vector spaces. So we have some concepts that I'll talk about. Let's start with the concept of a row space. A row space of a matrix is the span of its rows. We've talked about span in previous lessons. And the row rank is the dimension of this space, the number of linearly independent rows. So for example, we have this matrix here, 1, 0, 0, 1. This is the identity matrix in 2 dimensions, and that has row space equivalent to all of R2, and the rank is 2. These are 2 independent rows. Now here's a little bit different. The first 2 rows are independent, but the third row, we can write it as the sum of row 1 and row 2. So there's only 2 independent vectors here. And so the row space is a 2-dimensional plane in R2, and the row rank is 2. So I guess the next question would be, how do we figure out, if we have a more complicated matrix, how do we figure out what's the row space and what's the row rank? And it's something we've seen in the first lecture. It's a matter of using these row operations to reduce our matrix down to what's called the upper echelon form. I'll talk about that in a minute. But the elementary row operations are exchanging 2 rows. That doesn't change anything in terms of the dimension of your row space. Then multiplying a row by a scalar. Again, that doesn't change anything. And then finally, it's adding the scalar multiple of one row to another. And that scalar multiple could be a negative number, so effectively you could subtract. So these operations don't change the row space, and I want to prove that in the next slide. If matrix B is obtained from matrix A by a sequence of elementary row operations, then the row spaces are equal. So we have 3 cases. The first 2 are pretty easy. If we first of all, let the rows of our matrix A be V1, V2 up to Vn. If we switch the position of 2 rows to form matrix B, clearly you still have the same span. And if you multiply one of the rows by a scalar, then again you have the same span, because you can, whatever you can represent with these vectors here, you can just take the one that's been multiplied by a scalar and multiply by the reciprocal and span the same space. So these 2 are kind of obvious. The third one's a little bit trickier, but not too much. So we'll just take an example here concerning the third row operation. Suppose we change V2. It could be any of the vectors, but let's say we change V2 to the vector V2 plus a multiple of V1. Okay, I could have used I and J here, but and just to make it more general, but I thought this was sufficient. So the span of B, the matrix with rows V1, V, and then this substituted vector here, and then you continue on V3 all the way up to Vn, will include the vector V2 plus alpha V sub 1 minus alpha V sub 1, which equals V2, which implies that you can get V2 from a linear combination of what's in the span of B, which implies the span of A is a subset of the span of B. And then similarly, since V2 plus alpha V sub 1 is an element of the span of A, that implies that span of B is a subset of the span of A. And so since we've shown containment in both directions, we have the span of B equals the span of A. In order to determine the span of a row space for a matrix, we put the matrix into either row echelon form or reduced row echelon form. Row echelon form has two conditions. All rows having only zeros are at the bottom of your matrix. So you have an example of that here. And then the leading entry, that is the leftmost entry of every non-zero row, which is called the pivot, is on the right of the leading entry of the row above. So you keep moving to the right as you go down. And this is the leading entry here for this row, here for this row, and this row, and this row. And that's all you need for row echelon form. And you get your matrix into that form using the row operations I talked about on the previous slide. Then you have reduced row echelon form where the leading entry, the pivot, is a 1, and you have zeros in all positions wherever you have, other than the 1, of course, in all positions where you have your pivot being all other positions where your pivot is a 1. So you see here we got a 0. And in order to get from, in our example, to get from here to here, we divided this row by 3, this row by 5, excuse me. So we get 1s here, and then you can use the 1 here to eliminate the B using a row operation. Then the 1 here to eliminate the E and the C using row operations, and then the 1 here to eliminate the G, F, and D, again using row operations. So the point is, and let's look at it here, it's pretty clear that you have a row space of dimension 4. These row vectors are literally independent. There's no way of writing any one of these in terms of the other 3. And I think it's pretty clear just by observation. And so that's the goal, is to, if we want to determine the row space, is to get it, using row operations, to get our matrix into either row echelon form or, even better, reduced row echelon form. And I have a theorem concerning this on the next slide. So let's prove that the non-zero rows of a matrix in row echelon form make up a linearly independent set. We start with the matrix in row echelon form, and I admit this is not the most general way of drawing it, but it's kind of hard to represent any possible matrix in row echelon form. The point here is the procedure that I go through for this example, I guess you would call it, will work for anything in row echelon form. It's actually was a 1. I'm assuming a 1 here. That just makes it a little bit easier. So let V sub I be the ith row in the above matrix. So we have, this is V sub 1, V sub 2, and then there's K rows. And if there were 0 rows, we could just ignore those. They don't impact. So these are the non-zero rows that we're looking at, and there's K of them. And then we take a linear combination of these vectors, the row vectors, and set it equal to 0. And we know from our definition of linear independence that if all the A's, all the coefficients equal 0 and necessarily have to equal 0, then the vectors are linearly independent. So that's what we're going to show. So it's just a matter of multiplying this out, which is a little bit hard to see, but the first component, this is just one vector, keep in mind, when you add all these together. So the first component only is going to have an A1. Everything else has a 0 in that position, so you get A1 for the first component. Then the second component has A1 times M12. In the third component, it's A1 times M13 times A2. This one here. And then I color coded this to make it a little bit easier to see. Then the next component would be A1 times M14, A2 times M24. And I didn't put in the last element where you have a 1 here, but it's before K. I just called it A sub H. So that would be the last one. So these are all added together. And then you have some dots here, but then eventually you get to the column that has a 1 in the kth row, this one here, which I've coded in red. So it's A1 times M1J, A2 times M2J, and then all the way down to the one before here, AK minus 1, MK minus 1J, and then the last one would just be A sub K. And then we have some additional components, but we don't need those to show that all the A's are 0. So working from, and keep in mind, this vector here that we've computed equals the 0 vector. That's where we started. So each one of these components needs to equal the 0 vector. So first one's easy. We got A1 equals 0. The second one doesn't help much because even though we know A1 is 0, we just get 0 times M12 equals 0. So we don't get any additional information. But the third one gives us more information because we have A1 equaling 0 plus, so this is 0, and then plus A2, and this whole thing has to equal 0. So that gives us A2 equals 0. Then when we get to this one here, we know all the preceding A1, A2, all the way up to H minus 1 equals 0. So and this whole thing, this whole sum equals 0. That means A sub H equals 0, and then you just continue until you get to this element, this column, and that gives us that A sub K equals 0. So we've proven that all of the coefficients are 0, which means the vectors v1, v2, up to vk, that set of row vectors is linearly independent. And as I say, this isn't the most general form, but you can see how the procedure would always work because each column that has a 1 in it, a leading 1, pivot 1, is going to give you another equation that allows you the next coefficient to be equated with 0, and you just proceed down until you hit the number of rows you have, and you have a 1 there, and that'll give you the last coefficient being 0. Okay, so a little bit hairy, but hopefully you're able to follow this. And the important point is that we can take a matrix, reduce it down to row echelon form, and then we can determine the rank of the row space. In this case here, it would be K. Let's review what we proved in the last slide. In the language of vector spaces, the Gaussian elimination, which we did in order to get our matrix into the row echelon form, works by removing linearly dependent rows while leaving the span of the row space unchanged. The elimination stops when no non-trivial linear relationships remain among the non-zero rows. In summary, the Gaussian elimination results in a basis for the row space of a matrix. And we can do the same thing with the column space. We can define the column space of a matrix as the span of the set of columns, matrix columns, and the column rank is the dimension of the column space, the number of linearly independent columns. We'll prove later that the column rank and the row rank are the same. That's not obvious, but the column space and the row space span a space of the same dimension, which is a little bit surprising. So we'll get to that later. Then just changing gears a little bit here. I need a result that I'm going to use. So not necessarily related to what we've been talking about in terms of the row and column spaces, but we have this concept of a transpose of a matrix, and that's just the result of taking each row and making it a column. So the first row becomes the first column, the second row becomes the second column, and so forth. and that's called the transpose of a matrix. And we write it here is A superscript T. And then one other result related to this, if you have square matrices A and B, then the transpose of the product is the product of the transposes. So I won't prove that here, but that I'm going to need that result actually in this theorem here. So if matrix A is invertible, then the transpose is also invertible. This all implies that we're talking about a square matrix here. And the transpose of A inverse equals the inverse of A transpose. So since A is invertible, by definition, that means that there's some matrix, which we call A minus 1 or A inverse. When we multiply it times A on either side, we get the identity matrix. And then using this property we just talked about up here, we have the transpose of A times A inverse equals A inverse transpose times A transpose. And so the A inverse transpose is the left inverse. If you multiply this times A transpose on the left, you get the identity. In a similar way, we can show that A inverse T is a right inverse of A T or A transpose. Thus, A inverse transpose is the inverse of A transpose, and we have what's stated up here. Okay, so a little bit off the track of what we've been talking about, but as I say, I need to fit this in or use this later, and I just put it here. So just take a note of the result, both this result as well as this result here. We're going to need the concept of an elementary matrix in some of the following. So let's briefly go through that. It's pretty simple. An elementary matrix is a square matrix obtained from the application of a single elementary row operation, one of the three we mentioned earlier, to the identity matrix. Left multiplication, pre-multiplication by an elementary matrix, represents elementary row operations, while right multiplication, post-multiplication, represents elementary column operations. So I have a couple of examples here. I should point out that the elementary matrices could be of any size. It could be 2 by 2, 3 by 3, so on, 4 by 4. I just took 3 by 3 as the example here. So we take the identity matrix and we add 3 times the first row to the second row, and we get this here, and that's an elementary matrix. And then let's see if the description here holds true. So if we multiply this on the left times some general 3 by 3 matrix, we get the first row is just the same, unchanged. In the second row, when we multiply through, we're going to get 3A11 plus 1A21. Then 3A12 plus A22 and 3A13 plus A23. And then when we multiply this row times each column, we just get the same row again here. So the only change has been taking 3 times this row and adding it to this row, which is exactly what we did to create the elementary matrix in the first place. Now we can create this in another way. We can take the identity matrix and take 3 times the second column and add it to the first. We'll get the same thing, but I just want you to view it that way in this case here. And now we're multiplying on the right. And if you multiply on the right, you get A11 plus 3A12. And then getting this element here, you get A21 plus 3A22. And then A31 plus this times this, 3 times A32. Then when you multiply this row times the second column and this row times the second column, you're just going to get this again, and the same thing when you multiply this row times each one of these rows, I should say, times the third column, you get the same column again. So if you look at this, it's basically 3 times this row, column, added to the first column. which is what we did to create the elementary matrix here. Okay, and you can do the same thing with switching rows. I gave you an example here, so you might want to test that out on this matrix, multiplying on either side to see if it actually switches the rows or the columns. And then the other one is even simpler. That's just multiplying a row or a column by a negative or a positive number, a scalar, and see what that does when you multiply on the left or the right times a 3 by 3 matrix. Analogous to rows, elementary column operations, that is, exchanging columns, multiplying a column by a scalar, or multiplying a column by a scalar and adding to another column, do not change the column space. In addition, and somewhat surprising, or maybe somewhat surprising, row operations do not change the column rank. So let me give you some background on this first, and then I'll prove it on the next slide. So this proof uses elementary matrices, which we introduced on the last slide. We also make use of the fact that a matrix times a column vector can be represented as a linear combination of the column vectors of the matrix. So we have here an example. We have a matrix times a column vector, and it equals another column vector. And we can write this left-hand side as 1 times the first column plus 2 times the second column plus 3 times the third column. And if you add these together, you'll get the same result as multiplying these two. And that's true in general. You can have an n by n matrix times a column vector with n rows, and you can break it up in the same manner that we've done here. So the next part related to this is we note that a linear dependence relationship between the sum of columns of a matrix A is equivalent to the existence of non-zero column vector V such that AV equals 0. So for example, we have a different matrix from up here, but using the same idea of expanding in terms of the columns. We have column 1 is actually 1/2 of column 2. So if we took twice column 1 and subtracted it from column 2, we would, and 0 times this third column, we would show that the 3 columns are linearly dependent because we have this non-zero coefficients. Then when you multiply it times the column vectors, you get the 0 vector. So we'll make use of this in the proof, but we need this idea also. So let's prove our theorem that we stated on the previous slide, that the row operations do not affect the column rank of a matrix. So first note that the column rank of a matrix A is the size of the largest set of unrelated, i.e. independent columns in A. So we'll start with if E is an elementary matrix and B equals E times A, effectively a row operation on A, what we want to show is that A and B have the same dependent columns. Yeah, so after the basically after this operation on A, we don't change the column rank. Okay, so if AV equals 0 for some non-zero column vector V, then we can multiply B times V, and then substituting in EA for B, and then since we know that AV equals 0, we have that BV equals 0. So in other words, if there's a dependency between the columns of A, there also is between the columns of B, because we said that V is a non-zero column vector. And conversely, if there was a dependency between the columns of B, in other words, BV equals 0, where there's some V that's non-zero, not all its entries are 0, then AV can be written this way here. I'm just taking E inverse times B and then substituting that in for A. So we get AV equals E inverse times B equals V. In other words, AV equals 0. Thus, if looking at these two concepts together, thus if a set of column vectors in A is linearly dependent, then the corresponding set of column vectors of B is also linearly dependent and vice versa. And then from this, taking this statement into account, we can conclude that this means A and B have the same column rank. Okay, so this is sort of a stepping stone to the main theorem we want to get to, where the column rank and the row rank of a matrix are the same, and that's what we'll talk about on the next slide. I want to do an example of our theorem concerning the row space having the same dimension as the column space, which we'll talk about in the next slide. So shown below are the steps in putting a matrix into reduced row echelon form. The final result gives us a basis for the row space, the rows with a 1 in the leading entry. Further, since the final result is in reduced row echelon form, a basis for the column space is formed by the columns containing the leading entries. Thus, for a matrix in reduced row echelon form, we can find bases for the row and column spaces by taking the rows or columns containing the leading entries respectively. So let's just quickly go through the actual procedure in getting this matrix here on the left into this reduced row echelon form. So we take the first row from the second, and then twice the first row from the fourth row. So we get all zeros here, and then this is the computation. Then we'll divide this second row by -2. We get 1, 0, 1/2. Everything else is unchanged. And we'll take twice the second row and add it to the fourth. We get this. Then we see here that the third and fourth row are the same, so we can just subtract the third from the fourth row, and then divide 2 into the third row, and we're almost done. Then we take the third row from the first row to get a 0 here, and then take twice the second row from the first row to get a 0 here. And so just to repeat what I said up here, the 3 rows with leading ones are a basis for the row space, and the 3 columns containing the leading ones, so this column, and this column, are a basis for the column space. And we'll see that that's always the case, that you always have the row space and the column space that are of the same dimension. We'll prove that on the next slide. So let's look at our theorem, which I've mentioned a few times now. We'll give a proof. So the row rank and column rank, in other words, the dimension of the row space and the dimension of the column space of a given matrix, are always equal. And I'll kind of go through generally what I described for the specific example on the previous slide. If we put the matrix into reduced echelon form, then the row rank equals the number of rows with 1 as a leading entry, since that equals the number of non-zero rows. Further, the number of leading entries equals the column rank, because the set of columns containing leading entries consists of some of the vectors from the standard basis, and that set is linearly independent and spans the set of columns. So in reduced echelon form of a matrix, the row rank equals the column rank, because each equals the number of leading entries, leading ones. Theorem 19 from previous lecture and Theorem 22 prove that the row rank and column rank are not changed by using row operations and getting into reduced echelon form, So the row rank and the column rank of the original matrix are also equal, which is what we wanted to prove. In light of the above theorem, we can refer to just the rank of a matrix and not the row or column rank, since we know they're always equal. We have a theorem related to all of this. It's theorem number 24. Given an m by n matrix, so m rows and n columns, the following statements are equivalent. If the rank of A is R, then the solution space of AX equals 0, which is known as the kernel or the null space of A, has dimension n minus R. So we have the proof of this. It's basically a series of equivalent statements starting from this first one here and then ending with the second. So basically showing this is equivalent to this. So the rank of A is R if and only if the Gaussian elimination applied to A results in R non-zero rows. In other words, when we get the matrix A into reduced echelon form, which is what we've been working with in the previous slides in this presentation. And this is true if and only if, when we put in reduced echelon form the augmented matrix A with 0 in the right column has n minus R free variables. So from here to here is maybe a little bit hard to see, but I'll show you in an example exactly what's meant here. And then if you have n minus R free variables, that means that the solution space of the AX equals 0 is of dimension n minus R, which is what we wanted here. So let's look at an example just to emphasize this, in particular this one line here. So on this slide and the next, we'll do an example of the previous theorem. So we start with a matrix that's 4 by 7, so 4 rows, 7 columns, and then let's say that it's been reduced to, it's been put in reduced echelon form as follows here. So this is not actually the starting matrix, but I didn't want to go through the reduction. I just wanted to show you the final format here. So you notice we have a row of zeros, which is fine. We have a leading 1 in each non-zero row, and then the other elements in a row that has a leading 1 are all zeros. You notice there's zeros here, zeros here, zeros here. And so this is a reduced echelon form. And we can see right off that the rank of A is 3. There's 3 non-zero rows. And we were given that A has 7 columns. We can count them pretty easily here. And so we have R equals 3 and N equals 7. So those are the input numbers to our theorem. And what we want to verify is that the rank, the dimension of the kernel or null space of AX equals 0 is 4. N minus R is 4. So this is the part of the proof of the theorem that was maybe a little bit hard to see, and hopefully this will help you visualize that. So we take the system AX equals 0. This here is our A. Then X would just be, I have the transpose here because X is a column vector, but I didn't want to take up half the page writing as a column, so I just said X transpose is this. These are the components. And then the free variables are x2, x3, then another one here is x5, and then the last one x7. So we can make these whatever value we want when we parameterize the solution. From the first row we have x1, then we can take the these 4 actually, these for x2, x3, x5, and x7, we can bring those over to the other side. You remember we're solving now AX equals 0, so we've essentially added a column of zeros to the create the augmented matrix. So we get x1 in terms of these three free variables. Let's continue on the next slide. I brought our matrix over from the previous slide so we can refer to that. So from the second row, we have 1, 2, 3, 4. So we have x4 equals minus d times x5 minus f times x7. And then finally we have x6 equals minus g times x7. Then we can take our general solution to ax equals 0 and plug in the values that we found for x1, x4, and x6 into the vector for x. So you see here the first thing is, we took that from the previous slide, but this is what we solved for x1. Then x2 is fine. That's a free variable. x3 is a free variable. Then x4, we've written that in terms of x5 and x7. We plug that in here. Then x5 is a free variable. x6 we wrote in terms of the free variable x7, and then x7 is a free variable. Then going from this line to these two lines here, I couldn't fit it on one line, is basically just separating out the vectors containing the different free variables. So we have this first one has just the x2, that's just in the first component and the second. Then the rest have no x2, and then we do the same thing for x3, which is in the first component, not in the second, but in the third, and then not in the other ones. And we do the same thing here and here. And then we factor out an x2 from the first one, an x3 from the second, an x5 from the third, and an x7 from the fourth vector here. And then what we have is a linear combination of four linearly independent vectors. You can check these are linearly independent. They have ones and zeros in different places, so you can't write one in terms of the other three. And that basically says that the dimension of the solution space of ax equals 0 is 4. So it's basically depending on the number of free variables. You can write your x in terms of the free variables. You break it into pieces as we've done here, and then you have whatever the number of vectors are corresponding to the number of free variables, and they'll always be linearly independent. And so that's our example. We have one more theorem that kind of summarizes what we've done in this section, and I'll get to that on the next slide. We finished this lesson with a theorem that summarizes some of the results that we've talked about. So we're given an n by n square matrix A. The following statements are equivalent. The rank of A is n. The matrix A is non-singular, in other words, the inverse, A inverse exists. The rows of A form a linearly independent set. The columns of A form a linearly independent set. Any linear system Ax equals B has one and only one solution, X equals A inverse B. I'll give you some references to this theorem, which is sometimes known as the invertible matrix theorem. I'll put the references in the information to this video. And I won't do a formal proof here, but as I mentioned, this kind of summarizes some of the things we talked about. For example, 3 and 4 we know are equivalent because of the theorem we had about the row space and the column space being equal. And 2 and 5 are equivalent because you just multiply this by A inverse and you'll get the solution. The rank of A being n gives us that we have a set of linearly independent rows after we put it in reduced row echelon form. So I kind of given you a high-level proof already, but as I say, I'll give you some references if you want to look more into this. In fact, there's even more equivalent statements, some of which we haven't developed the theory to talk about yet. So it's actually quite an extensive theorem that when you see the references. But these five are things that we've already talked about. So I kind of gave you a reduced version of the invertible matrix theorem.